Let's take a polarizing filter and send some light through. Light consists of an oscillating electric field, shown in green. It also has an oscillating magnetic field, but we don't show that part. When the light passes through this filter, it looks like this. Notice that when the light goes through the filter, it's oscillating parallel to the transmission axis. In fact, any other component that this original light had gets absorbed by the filter. The percentage of the intensity transmitted is equal to cosine squared of the angle. And the angle here is the angle between the incident polarization plane before it passes and the transmission axis. We said that was 45. And this is an important trick. The cosine squared of 45 equals 1/2. So whenever you take light and you transmit it through a filter where the angle is 45 between the transmission axis and the polarization plane, well, we have to take that electric field oscillation with this amplitude and break it into a component. The component that passes through has to be parallel to the transmission axis. So if we look at just this half and we say, here's the amplitude, E max, that's the maximum electric field oscillation. How much gets through of this amplitude? E max cosine 45. And if we multiply the amplitude by cosine of 45, then we have to multiply the intensity by cosine squared, which we said was 1/2. Let's take 3 polarizing filters and send some light through. We'll say the light is initially vertically polarized. When this light passes through the filter, it now is oscillating parallel to the transmission axis. When this light passes through the next filter, now it's oscillating parallel to the transmission axis. And when it passes through the final filter, again, the oscillations in the electric field are parallel to the transmission axis. Notice the amplitude decreases as we go, because only a component of purple is parallel, and only a component of green is parallel to this axis, and likewise. And because only some of the amplitude gets through, only some of the intensity gets through. The percentage of the intensity that transmits equals cosine squared of the angle. So here's the first filter. The incident light, shown in purple, strikes the filter. Because these two are not perfectly aligned, only a component gets through. The angle tells us how much gets through, and we can use the equations to calculate. The component shown in green should form a right triangle with the hypotenuse shown in purple. If we put these lines, we see that the component is drawn correctly. It doesn't extend too far beyond the hypotenuse. That light, which transmits through the first filter, continues along until it hits the second filter. And again, because these are not perfectly aligned, only a component gets through. The angle says how much. We can check our component to see that it's drawn correctly by envisioning the right triangle. This blue light, which transmits through the second filter, continues on until it hits the third filter. Because the two are not perfectly aligned with each other, only a component gets through. The angle again can be used to calculate how much gets through. To check our component and see if we've drawn correctly, we put up those dotted lines, and yes, we can envision the right triangle. Let's work through an example where the initial beam, or the initial ray, has an intensity of 10 watts per meter squared. We know what happens as the light passes through each filter, but we're going to do the math using this equation. When that first ray of light strikes the filter, only a component gets through. The component is shown in green. We're going to make the angle 10. So the angle tells us how much gets through. If we take the cosine squared of 10, 97% of the 10 watts per meter squared get through. 0.97 of 10 gives us 9.7 watts per meter squared. The light then strikes the next filter, and again, because the two are not perfectly aligned, only a component passes through. The angle, which we'll say is 20 now, tells us how much gets through. The percent that's transmitted is 0.88. 8.6 watts per meter squared is 88% of 9.7. So this light continues on until it hits the final filter. Only a component passes through, and we'll say the angle is 30. So the percentage of the 8.6, how much of it gets through? The answer is 75%. So if we multiply 8.6 times 0.75, we get 6.4 watts per meter squared. To get from 10 watts per meter squared to the final answer, we had to reduce that intensity once for the first filter, a second time for the second filter, and a third time for the third filter. These values, 0.97, 0.86, 0.75, are the cosine squared factors. This is cosine squared for the first angle, and then for the second angle, and then for the third angle. And these factors tell us how much light we retain when the beam passes through each of the three filters. If you want to combine the effect from all three, you multiply all three together by the initial intensity. And when you do that, you get the correct answer of 6.4 watts per meter squared. As a final example, let's take unpolarized light from the sun and pass it through three filters. Because the light starts unpolarized, only half gets through the first filter. This first filter could be rotated in any angle, and we would still only have half of the unpolarized light making it through. Let's say the second filter is at 45 degrees to the first. How much gets through? Half of the original intensity. And if this is at 45 degrees to the prior filter, how much gets through? Again, half the original intensity. If we start with some amount I0, then we cut it in half when we pass through the first filter, and then we take this amount, and again, we cut it in half because we've got 45 degrees between these two. And then one final time, the angle between this polarization plane and the transmission axis is once more 45 degrees. So we cut this value in half again.